Okay, we're recording. So, so new section, new chapter today. We're going to talk about what's ultimately going to end up being kind of more of the same of what we did in chapter 6, except it's going to be in 3 dimensions, and it's going to involve, therefore, 3-dimensional objects. For example, surfaces. And in the same way that in, with Green's theorem and stuff like that, there were line integrals involved. We're going to have to eventually figure out how to define a surface integral. We're going to do an integral over surfaces, right? We've never done anything like that before. So, big challenge to figure out how to do that, and then, what resulting goodness comes out of it, what kind of, theorems and results and applications, and there will be a lot. But in order to be able to do that, we need to talk some about surfaces, and in particular how to parameterize surfaces. Okay, so here's the good news. Parameterizing surfaces is really pretty much a lot like parameterizing curves. When you parameterize a curve, position is a function of one parameter. Typically t, not that it matters. Parameterizing a surface, you have position in terms of 2 parameters. That's all there is to it. Pretty much. In fact, we've seen one of these before. If you look back to section 1.5, they talk about parametrizing a plane, and here's the formula that you'll find back there. In fact, we even had a homework exercise in probably that same section, I guess, where you had to basically kind of build up this construction to define I think it was a parallelogram in space, something like that. Y'all may remember that exercise. Anyway, the big idea is if you have a vector pointing in one direction parallel to the plane, and if you have another vector pointing in a different direction parallel to the plane, then notice that a scalar parameter s times that first direction vector gives you a vector of arbitrary length in that first direction, and then likewise a scalar parameter times the second vector gives you an arbitrary vector in the second direction parallel to the plane. And so by varying s and t, you can make these dark green and dark blue vectors as long as you want, or as short as you want, or if s and t are negative, they can go the other direction, what have you. And you're basically just moving as much as you want in whatever directions parallel to the plane, right? So with that in mind, if you start in the plane, let's say at a point x naught, right? Then moving parallel to the plane makes you stay in the plane. And so what we have then is this final point, right, given by this formula, will always be in the plane. And as s and t vary over all possible values, right, then this kind of moves you around over the entire plane, and this traces out, in a manner of speaking, traces out, kind of shades in, if you will, the entire plane. Okay, so notice we have a parametric surface because there are 2 parameters, s and t in this case. Okay, now, quick word of warning, tremendous analogies between parametric curves and parametric surfaces, but do be aware, when we did parametric curves, we like to think of the parameter as being time, right? It's just physically convenient, kind of geometrically satisfying, intuitively satisfying. Well, if you have 2 parameters, you can't think of them both this time. I don't know, it depends on what your favorite science fiction movie is, right? But I mean, typically, in normal terms that don't require, metaphysics, there's only one notion of time. Okay. Alrighty, so moving along, let's talk about some more rules for how to, tools, I should say, for how to parameterize surfaces. There are several. First thing I want to point out, there's a bunch of examples in the book, and they all have one, I think, pretty unfortunate feature. All of the examples in the book assume that you start with the parameterization and then you look at the algebra of the parameterization and then try to infer what the surface is that it's parametrizing. And what's unfortunate about that to me is that's usually the backwards of what you need, right? In practice, most of the time, the surface does not come pre-parametrized. The surface comes as something that you understand in a different way, either geometrically or by some sort of algebra or whatever. And then from that other form of understanding, you need to find the parameterization. So all of the examples I'm going to show you are of this latter category, where we know something else about the curve and we want to create a parameterization from it. And again, sadly, short of examples of that in the textbook. Okay, so here's my first example. This is my favorite parameterization, surface parameterization method, and that is the graph parameterization. You may recall we had a graph parameterization for curves. This is morally equivalent. It's the same main idea. The main idea is this. If you have a graph, as we do here, namely I've solved for one of the variables in terms of the others. Pause. I emphasize, you can't always do this. Not all surfaces are graphs. Very importantly, sometimes you fail the vertical line test or however you want to say it. But if you have a graph, if you can solve uniquely for, let's say, z, doesn't matter, but let's say z is a function of x and y. Whatever two variables are your input variables, let those be the parameters. That's the move. It's the exact same move as with parametric curves. It's just that with parametric curves, there was only one input parameter. Now there's two. Okay, so that's the big idea. Notice that plays out in this example. Here I have a graph because I've solved for z. Right? My input parameters are x and y. So as advised in this generic method, I let x and y be my input parameters. Notice. And having done that, notice plugging in these formulas for x and y requires that I use this formula here for z, and we're done. We have a parameterization. We have position as a function of two parameters. Everybody happy? Okay, so this trick, again, very, very similar to something we've seen before. Again, I like this next example just as to point out that there's nothing magic about alphabetical order. It doesn't have to be z as a function of x and y. It could be that for whatever reason you're solving for y as a function of x and z. It remains that you let the input variables, whatever you have not solved for, right, let those be your parameters. So notice if I were given this equation right here, notice I can't solve for z. It's just not feasible to solve for z, right? But I can pretty easily solve for y. Having solved for y, my input variables are now x and z. I then let x and z be my parameters, following the rule, right? Whatever your input variables, make those your parameters. And then continuing with these formulas for x and z, plug into there, and unavoidably we have to use this formula for y. And again, done. Parameterization, position is a function of s and t, and again we win. Okay. You can do this in other coordinate systems. Just like in with parametric curves, reminder, all you have to do this, for example, in, let's say, spherical coordinates, is step one, write down your conversion formulas. What are x, y, and z as functions of those, in this case now, spherical coordinates. We did this with polar back with curves. But same deal. Notice in this equation right here, I have a spherical graph. Right, position, one of these spherical variables given as a function of the other two. In fact, it's a function of it's a function of the other two where one of them doesn't even appear. Totally fine. And because I've solved for rho, I just let this dictate what my rho needs to be. There, and there. And notice, again, victory, right? Again, I have position as a function of two parameters. Now this time I'm using phi and theta as my parameters. I didn't replace them with s and t. I suppose I could have. There may be circumstances where maybe you might want to. But what's convenient about this is I don't have to, because there's no confusion of variables as it is. And there's something kind of geometrically convenient about leaving my parameters as phi and theta, because geometrically the parameters truly are phi and theta, and there's something kind of nice about being able to see that. So that's one of the luxuries of non-rectangular graph parameterizations. Anyway, okay. All right. This next example is a little obscure. It's highly manufactured. I don't really know how often this is going to come up, so I'm going to be very quick in talking about this example. I don't anticipate this being a big deal in this course or really much beyond this course, but I want you to see that there is an idea here, there is a tool here, and it can be useful. This is analogous to the examples that we did back in chapter 1, where we were talking about the bicycle wheel and the reflector on the bicycle wheel, and the bicycle rolls down the road and the reflector makes this weird pattern. And the big tool that we used there was vectors, right? Sometimes a position is a complicated, hard to understand function of time, but it's a sum of smaller, more elemental vectors that are much easier to understand. And so break down what you're interested in as a sum of vectors, and you win. So in this case here, now this is a weird example, I confess. We've got this surface here, right? And then now imagine that this is the someone's top of someone's head, and then we have hairs extending perpendicularly, right? So imagine they've grabbed one of those electric things, and it makes your hair stand on end, right? That does this to all of their hair. And what we want to do is figure out what is the shape made by, now let's do better than that, what is this shape made by sort of the tips of the hairs, right? So how would I parameterize this shape? In other words, how would I parameterize the shape of what their head seems to look like because of their hair sticking out? Okay, so how are we going to do this? Well, you can break this down with vectors, and specifically, we can ask, how do I understand position on this surface? And this is actually pretty straightforward. Notice that this surface is a graph. When you have a graph, you can use the graph parameterization. Cool, we just found position on that surface. We found this point here, right, as a function of our parameters s and t. So that part's straightforward. Next, I just need to understand this vector, right? And the punchline is, if I already know the green point, and if I can find the purple vector, then this dark blue point, in other words, points position on my hair tip surface, is just the sum of those. I just need to write green plus purple, right, to give me this, to give me dark blue. So let's talk about purple. What can I say about purple? Well, purple is parallel to this vector being perpendicular to our original surface. And how am I going to find this vector perpendicular to the surface? Well, I'm going to interpret the surface as a level set. Now, I want to remind y'all, all this stuff that we did back at the start of chapter 2, where it's very important to make sure to distinguish between what function is your surface a level set of versus what surface or what function is your surface a graph of, right? So very important to notice this distinction. Let's see here. So we are looking at a graph of that function, but we are looking at a level set of this very significantly different function, right? So a very, very important detail. These are different functions, and you got to make sure to pick the right one. You have to, if you're going to use the calculus of level sets, you better find a function whose level set is what you want. Okay, all right. So that aside, we have our our function whose level set is what we're talking about. The gradient is, I used the wrong color there, sorry. The gradient is easy to write down. I can normalize by dividing by its own magnitude. And we're in business. Right? We know this green point in terms of S&T. By the graph parameterization, we know this purple vector in terms of S&T by way of this gradient, normalized gradient trick. And green plus purple is what we want. And here you go. Green plus purple gives us the surface that we want right there. Okay, so again, not that this comes up that much, but I wanted to point out that the ideas that we've seen for parametric curves also show up in analogous ways for parametric surfaces. Okay, now here's a kind of a new one. This one is pretty common. This is a really regularly useful tool. It's a very clever idea. The idea is to create basically a new coordinate system for your surface. Very often this will present itself pretty naturally. So for example, let's look at this thing called a torus here. Right? Torus is the surface that is the kind of the outside part of the donut. It's where the glaze is on the donut. It's not the doughy part in the middle. It's just the surface, not a solid. It's just a surface. Right? So, but we casually call this a donut. How would I parameterize this donut? Well, again, I claim there's a kind of a natural, what I'm going to call coordinate system on this donut. I mean, imagine you were living on a weird shaped planet where where the planet was shaped like a donut, like this, right? And you had to create a coordinate system on that donut. Now, I propose the following seemingly very natural choice to describe location. If you want to know where you are, first let's talk about how much. That was not the color I wanted. How much do you go sort of around the handle of the donut, if you will, from horizontal, and then how far do you go kind of around the hole of the donut? It's almost kind of like a longitude and latitude, kind of, sort of, but for donuts. Right? So inspired though by the regular longitude and latitude for the Earth. So now, why did I think of this? I don't know. When you look at a donut, I mean, how else would you describe location? If you had to come up with a system to most conveniently describe points, locations on the surface of the donut, you wouldn't use X, Y, and Z. That's awkward, right? It's super weird. But just these two angles, that tells you where you are. So does everybody understand my coordinate system first? Everybody all right with that? Okay. Again, in the tool that I'm describing here of how you can use this to parameterize surfaces, this is something that you make up. This is not given in the statement of the problem. This is something that you look at and ask yourself, what would be convenient here? Okay. And then you can just use geometry to figure out where the corresponding point is. If you know your T and your S, what is the resulting point? And I argue as follows. First, let's try to figure out where, let's see here, I'll use purple. Where is this point first? And that point is actually pretty straightforward to, that was terrible. Let me try that again. This point, pretty straightforward to identify because that vector is just a constant, right? Whatever that sort of inside, anyway, that radius, if you will, of that aspect of the donut, right? And then plus this vector. I should really have these over here. So that plus elbow plus this And what can I say about that vector? Well, I know the angle t there, and as t varies, it just kind of goes around in a little circle, and that location of where you are on that circle is just a matter of a little bit of trig. And so think through the trig of that picture. It's just trig. So I know the green vector, I know the blue vector, and all together then I have a formula for the coordinates of that point P. Now we're not done. This is not what I need, right? That's just kind of the getting started. What I really want is the coordinates of this point, where my first coordinate is T but my second coordinate is S. This is, around the side of the donut a ways from this purple point that I've already computed. Is everybody on board so far? All right, so how am I going to take what I know about the purple point and turn that into the point that I want, namely, how am I going to get to this dark blue point? And I'm going to make the innocent observation that that's just going to be a rotation around the z-axis. Yeah? Is that all right? Okay, so how do we rotate around the z-axis? Well, this is really, in fact, old news. Rotating around the z-axis, that's a Math 218 problem, right? That's a geometric linear transformation. I know I've said this a million times, but this is really important. Math 219 does assume comfort, proficiency with linear algebra, and specifically, I'm going to make most use of geometric linear transformations like rotations. So remember, the big idea, all linear transformations are matrices. Matrices are understood by their columns. The columns are the images of the standard basis vectors, and you can figure out those images of standard basis vectors by just doing geometry in the picture. So, exercise for y'all to fill in the details. But this matrix here is what accomplishes that rotation. Okay. So, and we're done. Because we've already computed that the purple point, kind of in the xy plane, was this, through a vectors argument. And then the rotation was done by that. And then altogether, what we're looking for is that multiplied out. And you're going to, matrix multiplication is kind of annoying. But you write that all down and boom, there you go. So there's, believe it or not, kind of a weird formula to end up with, but this thing parameterizes a donut. Everybody happy? All right. So, big trick. Again, now there's a certain amount of geometry, and okay, don't get lost in the geometry. The big trick here, the big point is, we created a coordinate system that seemed natural on the surface. And once you have that coordinate system chosen, very clear, you got to be crisp and clear and unambiguous in your mind about what your coordinates are, then it's just a matter of doing whatever the necessary geometry is. And it'll be different for every question, of course, but this idea of creating coordinates is the big trick. Okay. Here's another one. Different trick. Totally. Again, I'm trying to fill up the toolbox, right, of how do we create parameterizations. Just like with parametric curves, it's not a single method. There's a bunch of different kind of tricks and tools, and just good to see all of those various tools. So here's another tool for your toolbox. If you have an existing parameterization, which very often you do, there will be something that's easy to parameterize or that you have already parameterized. And what you need to do is to figure out how to deform it according to whatever your circumstance is. So here we go. For example, an easy parameterization to start off with. Let's see, I'll do this in blue. The unit sphere. Right, unit sphere, rho equals 1. Not hard to parameterize. After all, this is a spherical graph. Rho is solved for. So just let phi and theta be your parameters and plug into the conversion formulas, and out comes this parameterization. Right, now that was an easy one. Straight out of the spherical graph parameterization, everyone's favorite surface parameterization tool. Okay. And now I can write that down in equations like this. These are the same. This is a vector statement of, and then an equation statement of exactly the same thing. Okay, so there's our easy existing parameterization. Now let's ask, what am I going to do? How am I going to make this? How am I going to parameterize this ellipsoid here? Now that one's not immediately easy. It does not have an easy spherical equation. It's not rho equals 1, and it's not rho equals an easy formula. This is weird, right? This is going to be a much harder thing to parameterize directly. Okay, but the nice thing about this is that it is easily related. There's an easy deformation between something I have parameterized and something that I now want to parameterize, and that it's just a matter of stretching, right? And remember the stretching, you can see the stretching in the what's happened to the equation x turned into x over a, and y turned into y over b, and z turned into z over c. So right, chapter 2 concept, this is literally just a stretched out sphere. Right? So once we realize what the deformation is, I can just directly use that to come up with my new parameterization. In fact, I can do this in two different ways. So let me remind you, we had this formula here, parameterizing our sphere. I had, for example, x, y, and z. And I know what I want to do to x, y, and z. I want to stretch them. Literally, I just want to make those coordinates bigger by factors a, b, and c. And so, okay, I will literally make the x, y, and z coordinates bigger by factors a, b, and c, because that's what stretching is. Everybody good so far? Okay. Now, seemingly contradictory. Just at a glance, this looks counterintuitive. What if I were to take this form of the spherical parameterization and do the stretching there? And wait a second, stretching there, we replace x with x over a, right? And y with y over b, and z with z over c. That's our old rules for how to stretch things out. And at a quick glance, wait a second, how come we multiply on the left side of the page and we divide on the right side of the page? It actually seems kind of wrong until you notice that, in fact, these are all the same. This and this are exactly the same. This a here cross multiplies to be a multiplicative factor on the right-hand side. So this is just kind of two different versions of the same thing. So take your pick, whichever one you like better. Again, when you have a take-your-pick situation, I think it's important to try to understand both sides, both of the different sort of ways you can approach this. You never know which one's going to be more useful in what circumstance. But in any given circumstance, you can choose to think of literally making the formulas for the coordinates stretched out as they're supposed to be, or you can take the replacement strategy for the variables, not the formula for the variables. It's just a different way of doing the same thing. Okay, so big punchline though. Again, we started with an easy parameterization, and we got to our new parameterization by recognizing what was the nature of the deformation and then just deforming accordingly. Right, so really useful trick. This ellipse would have been very hard to parameterize otherwise. Everybody okay? Okay. Okie dokie. Good deal. All right, so I've already made this comment here, by the way. So the book does give some more examples, and by the way, I like the book's examples. It's just that they're examples in sort of the wrong direction. Right, so I encourage you to take a look at the book's examples, and you might even, if you want to turn the book's examples into exercises, just turn them around for yourself. Start at the end of the example, see what they've concluded that surface is, and then try to figure out for yourself, how would I create a parameterization for this surface, right? And then don't read the example. You can sort of give it away, right? And try to come up with it on your own. Okay. All right. Okay. So moving along. A clever idea. Suppose you have a parametrized surface. So position is a function of S and T. So we've got a position as a function of two parameters. Here's seemingly kind of an innocent observation. If I were to fix T, if I were to make T constant, T is not allowed to change now. Right? If you think about it, what we have then with T fixed is I have position as a function of, well, effectively really only one remaining actual parameter. S is the only remaining true parameter if I've fixed T. T is not allowed to change. T is now a constant. Well, there's really only one actual variable. And of course, when you have position as a function of a single parameter, that gives you a parametric curve. So, nice little idea. So this is called a coordinate curve. This in particular is the S coordinate curve, because S is the parameter for this S coordinate curve, because T has been held constant. Right? Okay, and likewise the other way, you could fix S. That gives you the T coordinate curve. All right, let's see an example. What does this look like? I'm going to use the unit sphere. We've talked about the unit sphere before. Here's how you parameterize the unit sphere. Again, spherical graph parameterization. This comes right out of rho equals 1, right, per one of our early examples. Okay. Okay, so let's make the theta coordinate curve. We're going to start off with the theta coordinate curve. Okay. To get the theta coordinate curve, remember I have to fix the other variable. The other variable is phi. So I'm going to fix phi as pi over 6. So you'll notice phi not allowed to change now. Phi is fixed at pi over 6. Geometrically, if you want to, you can think of that as phi being kind of an angle like this, and if it's fixed constant, then you are confined to this cone, if you want to think of it that way. Okay, so what happens then with theta? Well, theta is allowed to vary. Theta can kind of do whatever, and so I'm looking in the vicinity, by the way, of this point here, that point belonging to that point on the curve, and as theta varies, as theta kind of, goes from a little less than pi over 4 to a little more than pi over 4, notice that just drags me around I guess you'd call that a latitude line on the sphere. So that's called the theta coordinate curve at that point. Does everybody see what I mean? This is mostly terminology and notation. Okay. All right. Likewise, we can talk about the phi coordinate curve. If you want to make the phi coordinate curve, you've got to fix theta. So theta now, not allowed to change. Theta is fixed at pi over 4, which of course means that we are confined to a particular theta cross-section. Wow, getting some thunder out there. So in that theta cross-section, now let's ask the question, what happens if I vary phi, right? If I'm looking at the phi coordinate curve, phi is allowed to change from maybe a little less than pi over 6 to a little more than pi over 6. And as phi varies with theta constant, I get that curve right there. Is everybody with me? All right. Okay, so clever idea because of the following observation, and that is that partial derivatives of the parametrized surface become velocities of the coordinate curve. Now let me walk you through why that is. You kind of have to sort of think through what this all means. Let's talk about velocity of a coordinate curve. Well, a coordinate curve, the first thing you do to make a coordinate curve is you fix one of the inputs. Well, that's also the first step in taking a partial derivative. You fix the other input variable. Right? And then what's the next thing you do to take a velocity of a coordinate curve? Well, you take the derivative with respect to the remaining input parameter. That's what you do when you take a partial derivative. You're taking a derivative with respect to the remaining unfixed input variable. Right? So it just happens to be that they're exactly the same process. Right? So a partial derivative of the parametrized surface is just a velocity of a coordinate curve, and that's a great way to think about it. It's a really useful point of view. And so, for example, if I were to do something like this, if I were to write down what is, let me use the pencil, what is x theta d theta, well, let's look at this thing. X theta is a partial derivative of the parameters of the parametric surface, which I've just agreed is a velocity of the theta coordinate curve. And so looking at this green thing here, what is this green thing? Well, I'm multiplying velocity times input change. Again with the elbow, I'm sorry. Let's see here. Velocity times input change gives you output change. So this thing here, this product, velocity times input change, is literally just the corresponding output change vector parallel to the surface. How are we doing on that? Does everybody follow that reasoning? Velocity times input change gives you output change. So this is an important construction. And then, by the way, likewise for the other one, let's see here. So this thing here is that little displacement in the phi direction. Right, so altogether then, what I've got is a nice little geometric connection, and I think I've even drawn this down here. Yeah, here we go. So we've agreed that this velocity, that input change gives you this output change, and that this input change gives you that output change. And as a result, let's see here, this little piece of area here has as its image this little piece of area there. So green area goes through this surface parameterization to produce approximately that blue area there. Now let me write that down. The blue area. Well, the blue area is an easy formula. The blue area is the magnitude of the cross product of those two edge vectors. I mean, it's a parallelogram in space. So this is an old formula from 218 probably, but certainly from chapter 1 in this course. So that blue area, there's the formula. It is anyway. And notice I can factor out the I can factor, I want to do this with a highlighter. I can factor out d phi, and I can factor out d theta. They're, after all, just scalars. So they factor right out of the cross product. They factor right out of the magnitude. And lo and behold, that gives me the blue area as a factor times the green area. So let me sort of re-highlight here. This blue area on the right-hand side is a scalar factor times the green area, and that makes this scalar factor here my stretching factor. So just by kind of playing some geometric games with these parameterizations and clever ideas about coordinate curves, etc., we have ourselves a surface area stretching factor. And what that means is that I'm going to be able to do integrals on the surface of the sphere by pulling back through the parameterization and turning those into integrals over here. Everybody kind of see the strategy, where we're going with this? Okay, let's see. Let me try to leave, I want to leave the green and the blue. Let's see if I can delete the other stuff here. There we go. Okay. All right, so Stretching factor is that purple thing there. And in fact, let me go ahead and put a circle around this. It's a lot of students maybe get a little confused as the precise details. It's not just that this is a cross product. You got to make sure to recall it's the magnitude of that cross product. Okay. All right. Okay, so there's our stretching factor. Isn't that nice? Now, that said, it does turn out there is something of specific interest about the cross product itself. I emphasize that's not the stretching factor. The cross product is a vector, after all. Right? It's the magnitude of that vector that's your stretching factor. But this cross product itself, still interesting. If you think about it, x phi and x theta are both tangent to the surface, and so that means that this cross product is perpendicular to the surface. And that's going to end up being extremely useful later on. And hard to see right now where that's going to come in, but it is going to come in and be a big deal. So in anticipation of that, we make the following definition. That cross product, we're going to call that capital N. And now there's a little bit to say about the terminology. I like to call this the parametrized normal vector. Let's talk about the terminology. It's a normal vector because, of course, it's perpendicular to the surface. We talked about that, so of course it's a normal vector. I like to call it the parametrized normal vector specifically because notice this comes out of the parametrization. If you look at this formula, you are taking the partials initially of the parametrization. There's nothing canonical about this vector as far as the surface is concerned. The underlying surface, you could parameterize it a lot of different ways, and that would give you a lot of different capital N vectors. They're all valid for their parametrizations. It depends on the parameterization, and thus I call it the parametrized normal vector. I hope that makes sense. Does that seem like a reasonable choice? Because it comes out of the parameterization. Now, the book disagrees with me on this, and that's fine. The book chooses to call this the standard normal vector. And here's my problem with that. It's not intrinsically standard to the surface. It just isn't. It's standard to the parameterization. But people don't tend to think in those terms. I think students tend to think of the surface as being the thing, and the parameterization is a kind of one of many tools that we can use to describe that thing, but in particular, this thing in question is not truly standard to the surface. So I think calling it the standard normal vector is a little risky move, possibly confusing, and so I don't use that term, but it is in the book. You are allowed to use that. I find it unsatisfying myself. Okay. All right. Okay, so with all of this in mind, notice that means that our area stretching factor is just the magnitude of capital N. Nice little compact little formula. A really useful fact, right? Given a parameterization, we have a formula for capital N. The magnitude of capital N is the area stretching factor in that parameterization. Okay, let's use this to compute something. All right. Okay, all right. It's fine. Okay. All righty. So let's suppose I want to compute the area of the unit sphere. Now, there's different ways to do this, of course, right? You could do this with a clever arguments about single variable calculus, and that's all fine. The purpose of this example is not to find the answer, right? I know we already know the answer. The purpose of this example is to show our new tool in action, right? And so here we go. First, we parameterize the unit sphere. Rho equals 1, spherical graph parameterization, right? Does everybody remember that one? Right. Okay, now here's our formula for capital N. Apparently I'm going to need to know x phi and x theta. Okay, well, I'm going to have to take then the phi partial to get x phi, and I'm going to have to take the theta partial to get x theta. And then I'm going to have to take those things, right? I'm going to have to take this and cross it, apparently, with this, right? Because crossing is how you find capital N, and some trig to be done, and some Pythagorean identities to be noticed, and et cetera, et cetera. So there's a little bit of annoying work to be done there, but boom, there is our capital N vector. That then is our stretching factor as we pull back through this surface parameterization. And so to find the area, I'm sorry, got ahead of myself. This is my capital N vector. This then is the vector whose magnitude, see how easy it is to make that mistake? It's the magnitude that is the stretching factor. So more Pythagorean trig identities come up, right? And that magnitude ends up being sine phi. By the way, this is a good exercise to do. Everybody should do this one once in their lives also, right? There's various little sort of standard computations to which the answers are known and written in the book, but there's something healthy about doing those computations yourself. So I hope you will take the couple of minutes that it'll take you to do that computation and see how this plays out. By the way, for whatever it's worth, I have on past exams, you'll see this on my old past exams, which of course are public. There have been test questions which were to do that calculation. So it's a really good exercise. Give it a shot. Okay. All right, so we're in business. Now we're about to compute the area of the sphere. I know that the total area is the sum of the little pieces of area. I know that each little piece of area is stretching factor times pullback area. Right? Here's our stretching factor that we just computed. Right there. Everybody with me? Okay. And let's see, to define the entire sphere, of course, I need theta to go all the way around, because I want the whole sphere all the way around, but I also, furthermore, want phi to go all the way from top to bottom, because I want, again, the whole sphere. Right? And we're in business. The stretching factor, again, previously computed, sine phi. And we have an easy integral to compute, and the answer is 4 pi. Which we already knew. Again, the purpose of this is not to find the answer. We knew the answer. The purpose was to see our tool in action. Okay. Is everybody okay? Okay. Good. Okay. Well, so this is mostly a summarizing page here, except for one little fun example at the bottom that we may or may not get to. But recall, we talked about a parameterization of a surface. We have our parameters, S and T, that are the inputs. That makes our parametric surface. We talked about these partial derivatives of the parameterization and how they allow us to compute our capital N vector. Right? And I'm going to make the slight supplement here to point out that the capital N vector can be thought of as a unit vector times the magnitude of capital N. Right? That's just a direction times magnitude observation there. Right? So nothing too surprising about that. This is going to end up being useful a little bit later on. Then you can multiply this out. Again, we have this formula for what capital N is, and you can just crank it. I haven't previously cranked this. I haven't actually multiplied out what this cross product is, but XS, of course, is just these partials, and XT, of course, is just those partials, and you can just take a deep breath and write down the formula for that cross product. And what you're going to notice is kind of a weird, unexpected coincidence happens. The coordinates, as it turns out, the coordinates of your capital N vector, they're all little bitty stretching factors, little 2x2 stretching factors, which seems like a coincidence, because there is no 2x2 change of variables in the picture that we've drawn. So a little bit, that's weird. By the way, it turns out it's not at all a coincidence. There actually is there are 3 hidden 2x2 change of variables in the picture. That's why these change of variable stretching factors come up. I would love to talk about that. We do not have time in Math 219, sadly. If this were a full year course, I would totally talk about that. But we can't. But it's nothing, you don't need to know it, but it's just geometrically cool. So the very last thing, I'm out of time. Okay, so we will draw the line right here, and we will do the very cool last example on Monday. Y'all have a great, holiday weekend if you're into that. Okay, see you later.